Hello, this video is going to talk about tree and Venn diagrams. And for this video, we're going to start with the tree diagram. And hopefully you remember these from our Algebra 2 class. So these are especially useful in probability topics when we want to show what's happening with a visual. And it won't be a Venn diagram, but it's going to be a tree diagram showing the branches of what could happen. So for example, we have an urn with two balls, one red, one blue. Draw two balls one at a time with replacement, which means we put the first ball back. So that we put the choices down here. So the first branch goes here. It could be blue or red. Then we put the ball back, and it could be another blue or red. And so our outcomes are here: blue, 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 red, red, blue, or red, red. And that's just a very simple tree diagram. We could put probabilities on there and calculate all of that. Let's go to a more complicated one. And so over here, we're going to have an urn with 11 balls, and 3 are red and 8 are blue. So we're going to take 2 balls again with replacement, and we're going to draw our tree diagram like this. So first draw, there are 3 branches that would go to red, and so we're going to put those 3 branches together with 3 red, and 8 that go to blue. So we would put 8B for 8 blues. Now, whenever we draw first, we put it back in, and then we redraw it again. So the second draw looks exactly the same. It's just coming off of the first draw. So there's 3 red and then another 3 red. So there's going to be 9 different ways to get red, red. There's a lot of ways to get blue, blue because there's a lot more blue balls here than red. So 64 ways to get blue, blue. And here's blue, red, and red, blue. And we can see the total of all of these. If you add up 9 and 24 and 24 and 64, those add up to 121 because it's 11 and 11 multiplied by 11 because we have 11 choices here, 11 choices here, and we get 121 total. All right, so we're going to use this to calculate some probabilities. All right, and so here's our sample space. Sample space is all of the possible outcomes, and this is explaining what all of our pieces mean. So 3R represents getting the 3 different ways to get a red. So you can get red number 1, red 2, or red 3, and 8Bs could be all the different 8 blues, and so on. 9RR is all the different ways to get the 2 reds. Okay, so here's our sample space. As I said, adding up our 9, 24, 24, and 64, we get 121, which makes sense because 11 times 11 is 121. Now we can list out some outcomes. List the 24 outcomes, 24 BR outcomes. Well, that would be really tedious, but there they are. Now we want to calculate probabilities, the probability of red, red. So to do that, what you can do is calculate your probabilities. So we want to land here. So we can think, what's the probability of getting there? Well, to get a red on the first draw would be 3 over 11, 3 elevenths. And then to get red on the second draw would be another 3 over 11. So we could take our probabilities 3 over 11 and multiply it by 3 over 11. We get 9 over 121. Remember, on fractions, you multiply the numerators together, put that up top, and multiply the denominators together, put that on the bottom. So we could calculate it that way, multiplying the probabilities. But another way, since we have already calculated the total sample space as 121, we could just write it as 9 over 121 because we know there's 9 ways to get red, red. What's the probability we get one of each, red, blue, or blue, red? So that's here and here. So we just take those 2 probabilities, or 2 outcomes, add them together to get 48 over 121. Or we could take the probabilities, 3 elevenths, 8 elevenths. There's our first one, plus 8 elevenths, 3 elevenths, and then we add those together. 2 ways to do it. Calculate the probability of red on the first draw and B on the second draw. So red on the first draw, 3 elevenths, and blue on the second draw, 8 elevenths. So we take 3 elevenths multiplied by 8 elevenths, 24 over 121. Or we could take that total, or that 24 total out of 121. Using the tree diagram, calculate the probability of red on the second draw given B on the first draw. This one's an interesting problem. So red on the second draw, and this says given B on the first draw. So since it says given B on the first draw, we're immediately looking right over here. We don't care what happens over here. So given B happened on the first draw. So boom, right now we're only looking right here. So given B happens means B has to happen. So over here we're looking, what's the probability we get red on the second draw? Well, it's just 3 over 11 again. And there we go, 3 over 11. And you could do that using probability as well. You could take this, so here's the 24 ways we do that. Out of the total of these two together would be 84 or 88. And 24 divided by 88 is 3/11. Probability of blue, well, that's just all the ways to get blue, 64 out of 121, or 8/11 multiplied by 8/11. Calculate the probability blue in the second draw, given R on the first draw, so red on the first draw. Calculate the probability of blue on the second, so that's just 8 out of 11. All right, so that was a tree diagram. Hopefully that makes some sense. We'll talk a little bit about Venn diagrams next. And this Venn diagram, we're going to actually have specific numbers involved. And we could go ahead and calculate some probabilities involving these numbers. Or we could use letters. And we can see the intersection, we can see the overlap, right? The only intersection they have is that 6 in the middle. But the union of all of this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, all of those. And then 10, 11, 12 are on the outside. And we could do the same thing with some colors too. All right, this is the probability of getting 5 different cards, no 2, 3, or 4 cards at the same value from a standard deck of cards. And here's a standard deck of cards if you're not familiar with it. And so to get the probability of 5 different cards, let's think about this. Let's first of all just draw a card. And do they say we put it back? I think we keep it out. Yeah, we have to keep them out because we need them to match. Okay, so the probability, well, we first of all draw a card, the Queen of Hearts. Now we need to draw a second card, and the second card can't be a queen. We want it to be a different value, so it can't be a queen, and there are only 3 queens left. There's 52 cards in a deck, and as we see here, we took out the Queen of Hearts. There's 3 other queens left, and there's 48. So there were 52. We took one out, so there's 51 cards, and 51 minus 3 would be 48. So there are 48 cards that we could pick from to be good cards. So we take our first card, then we multiply it by a no match. Then we need the third card to be different from the first and the second. So suppose the second card, we drew a king. So now we've drawn a queen and a king, and we're down to 50 cards left, and we don't want to match with any of the 6 that are bad ones, right? The 3 queens and the 3 kings. So there's 44 that are good ones. So suppose we have a queen, a king, an ace. Then the fourth card, down to 49 cards left. And we don't want to have the queen, the king, and the ace. So that would be just 9 different cards that are bad cards. So that's why it goes down 9 to 40. And it goes down all the way down to our last draw there. And that's how we calculate. So about pretty much a 50-50 chance of having a deck with no pairs or more. We could do that with probability of 10 people in a room. Nobody shares a birthday. I just looked at some COVID data related to this. The probability of 10 people in a room, what's the probability nobody has COVID? And depends on the county, but here we are for birthdays. So to do this, we do it just like our card example. Remember, 365 to the 10th just means 10 365s all multiplied together on the bottom. So the first person we just pick. Like my birthday is January 31st. So right there, I'm the first person. Then we need to pick another person. We need them to not have my birthday. So they can have 364 days to pick from out of the total of 365. So we need that to happen. Then the third person, we need them to not share my birthday or the second person's birthday. So that number goes down by 1. And it goes down by 1. And by the time we get to the end, that person, the 10th person, needs to share no birthdays with all 9 people there. That's why it drops down to 356. And if we calculate all of that, we get about 88%. All right, so that is a little video on Venn diagrams and tree diagrams. Hopefully it made some sense.